This video is going to help us to figure out how to find the line that best fits our data. Previously, we've learned about what line will be the best line, but now the question we need to think about is, how do we find that? Right? How do we find the line that best fits our data? How we'll think about it is we'll go back to a basic line, something we may have learned in high school or, I don't know, finding the line between two data points. If we remember that catchy equation for line, it was y equals m, which stands for our slope, x, which is our x variable, plus b, which is our intercept. Now, to find the slope, we may have remembered that catchy phrase, rise over run. So we look at this distance. And so here we see that our slope is representing rise over run, which in this case we actually decreased. We went from 3 down to 1. So we actually decreased by -2. Our run is we went from 1 to 2, so our run would be 1, therefore our slope equals -2. So essentially what a slope measures is change in y, so change in the y direction, over change in x, change in the x direction. So for our equation right now, we'd have y equals -2, which was our slope, x plus our intercept, b. Well, then what we can do is say, hey, we know a point on our line, right? We have 2 points on our line. What we can do is plug one of those points in. So let's plug the point 2, 1 into this equation. If we were to do that out, x is 2, y is 1, and if we were to solve for b, we'd have b equals 5. Therefore, our overall line would be y equals -2 x plus our intercept of 5. And this would be our line. We found the slope doing change in y over change in x, and we found the intercept by plugging in a point on your line. Now, while we'll do something slightly different to find our line of best fit, the concepts what we just learned are going to be exactly the same. The issue we have now is we don't just have 2 perfect points going through our graph. We now have a bunch of points. So we can't take that same approach. However, we need to find the line that best fits our data. So here's what we're going to do. Let's think about our slope. Now that we have a bunch of points, we can't find the exact change because there's all these different points. What we can do, though, is find the average change in y over the average change in x. We want to find the average change in y over the average change in x. Well, what gives us an average change? Hopefully you're going to be familiar with this term, the standard deviation. Right? If we were to think of the standard deviation, that measures the average distance an observation is from the mean. So instead of distance, let's change that word to change. Standard deviation, the average change an observation is from the mean. And that's exactly what we're trying to do with this slope. Find the average change in y over the average change in x. If we were to think about the average change of x, the standard deviation of x, and I'll write this formula out here, it was the summation of xi over the mean squared. We look at those average square distances and then we divide by n minus 1. This gave us the average change in observations from the mean. We could do the same thing for y. Find the average change of y, the standard deviation of y. So now all of these notational pieces are in terms of y. All right, and if we remember, we squared those distances because we didn't want it to sum to 0. Where did we also talk about that? With our residuals. Remember, we needed to square our residuals because they also would sum to 0. We can see how the standard deviation and summing these squared residuals have some things in common. We sum those residuals, they sum to 0. If we were to sum all the observations minus the mean, that also summed to 0. That was the reason why we squared those distances. Also the reason why we squared our residuals. Square all those distances. The big question that we need to think about, though, is why did we subtract all of our observations from the mean? Why couldn't we instead subtract all of our observations from the median? So if we were to look at that numerator, standard deviation, the average distance, the average change in observation is from the median. Standard deviation, the average change, the average distance in observation is from the number 2. Standard deviation, the average distance, the average change in observation is from the quantity x bar plus 2. I mean, why did we subtract everything specifically from the mean? Why couldn't we have chosen another number, another metric to find our standard deviation? Average change in observation is from whatever we want. Why is the mean being used? Well, here's why. Suppose we have 3 data points. So I'm going to write these data points. 1, 2, 3, 4, 5, 6. Right, so we have these 3 data points. 1, 2, and 6. If we were to find the mean of these data points, x bar, the mean would come out to be 3. 1 plus 2 plus 6 divided by 3 becomes 3. And then what we do is we say, okay, how far is each observation from the mean? If we were to do this out, we'd do 1 minus 3, we'd square that distance. 2 minus 3, we'd square this distance. And then 6 minus 3, we squared this distance. If we were to sum all these up, we get 14. Why is that important? Well, let's just kind of see what's going on here. Let's instead do the same exact thing. We have these data points. 1, 2, and 6. But now, let's do the same exact thing, but subtract everything from the median. So imagine this term was the median. Again, we could have chosen any other arbitrary number. So the median for these 3 observations would be the middle number, which would just be 2. So our median here is 2. And let's do the same thing. How far is each observation from this value? So we have 1 minus 2 squared plus 2 minus 2 squared plus 6 minus 2 squared. And if we were to do this out, we get 17. What we'll notice, and what I want to kind of highlight here, is look at these values. Again, this is just the numerator portion of our standard deviation. But look at these values. When we subtracted everything from the mean, we got a smaller sum of square distances. When we subtracted from the median, we got a bigger sum of square distances. Why is this important? Well, how are we finding the line that best fits our data? We're trying to minimize the sum of squared distances, of squared residuals. And what did we just see right here? When we subtracted from the mean, we got a smaller sum of squared distances, of squared residuals. Subtracting values from the mean will minimize your squared distances. This is why we find the standard deviation subtracting from the mean. It minimizes your distances. Any other number in the whole entire world other than 3 in this set of data, 1, 2, and 6, you will get a bigger sum than 14. Any number in the whole entire universe. This is why this concept is so important, because we're minimizing our distances all while finding the average change of y over the average change in x. This will give us the slope that best fits our data.